Hello everyone, hopefully you had a great night yesterday, as we did. So forgive us if we'll make a few mistakes here and there, and I would like to introduce us for a bit. This is my colleague Stefan. He will be the Docker guy in the talk, and I'm Rafal. I'll talk about Elasticsearch a bit through the talk, and today you're going to learn a bit about Elasticsearch and Docker, Docker and Elasticsearch working together, if it's love or hate.
Yeah, thank you. So you heard the introduction song, and this is a mix of two music styles, and what we have today is Elasticsearch and Docker. Both tools have clustering capabilities, and so the question is, do they work well together? For us as a company, Sematext, we are well known for big data consulting for Solar and Elasticsearch. During that consulting work, we developed a product for performance monitoring and log management, and that resulted in a product called the Sematext Cloud that gets together metrics and logs in one platform and creates alerts according to your needs of the operations. So we have
So as I mentioned, we'll like to talk a bit about Docker and Elasticsearch, and I would like to ask a question initially. Who from the audience, from you, knows and uses Docker? Yay, great. And Elasticsearch? Okay, so we have a bit of explanation. So we'll start with a few questions between ourselves, like, Docker is dynamic and Elasticsearch is dynamic as well in its nature. So can they actually work together?
Yes, it should. Docker is a process manager. It just provides isolated environment for processes with their own file system and own resource management. What should be the problem?
Dynamic environment. So if I have to put IP addresses of the master nodes to all the other nodes, can I do that?
Yeah, well, Docker provides you a dynamic IP address for every container that starts. The issue with Elasticsearch is you might not know this IP address, so you need another mechanism like DNS Roundrobin, to give Elasticsearch a DNS name or something to find the right nodes.
What about the storage? Elasticsearch needs storage, and it doesn't want it to be volatile, right? To disappear with the Docker container going down.
Yes, Docker is good for stateless applications, having no storage. That's excellent. It scales like hell. Like you start new processes, and you have more processes running. In case of Elasticsearch, you need then also scale the storage. And that's the reason we suggest to have one node with a mounted local storage. There are also storage drivers for Docker, and those might use a network, and you get additional latency, and that's bad for Elasticsearch performance. So the whole Elasticsearch cluster gets slower when you use a network-based storage. So we recommend local storage for that.
Okay, so those are the questions that we would like to get the answers for, and that will allow us to actually give you the answer if it's a love or hate, or you decide yourself after seeing some of those answers being, actually questions being answered and with a given reasons. But we would like to start why we use and why we like those technologies that we would like to introduce to you today and to talk about today.
Yeah, so I'm a big fan of Docker since the very beginning. I used it in the lab with very early versions. And the nice thing on Docker is it can package applications in one image, and then it's easy to distribute, and people can run applications. They don't need to know how to install. They just run a Docker image and specify a few parameters for configuration. So that simplifies a lot the process of deploying applications. The second argument you hear a lot is like Docker versus virtual machines, and because Docker is managing processes, it really provides a higher density of applications you can run on a single machine. There are more things like you could manage resources like networks or CPU and memory for every process separately. So you can build application stacks that run together on a single node, or you use orchestration tools like Swarm or Kubernetes to distribute the workloads over multiple nodes in your network. So you build a new cluster only made to run multiple applications on Docker.
Okay, so no more text for now. Let's start with the architecture of Elasticsearch and why we like it, why we like working with it, and what it's all about. It's a search engine based on Apache Lucene library, an open source full text search library that allows you to index your data and search through it. It's written in Java and written with distribution in mind. So whenever you start it, you get a fully working cluster even with a single node, and that can scale, and that can scale easily. However, to know how to scale it and to understand the architecture, we have to go through a certain amount of information. I'll give that information because not much of you are actually users of Elasticsearch. So Elasticsearch has a notion of types of nodes. Let's start from the right side with the master nodes. Those nodes are the brains of the cluster. They are there to operate on the metadata of the cluster and enables it to work properly. For example, if a new node joins the cluster, or an index is created, or some things change, like your data structure, you add a new field, that's all a part of the master work to do. The master work, there is always a single master inside the cluster, the rhymes. Though to have a fully fault-tolerant and highly available cluster, we need at least 3 of them, and 3 is usually enough. So 3 master servers out of which one will only do the work, and the rest will be on a standby mode in case the main master fails and just go away for some reason. Garbage collection, node being down, container being down, or anything like that. From resources perspective, master doesn't need much. It needs some CPU processing power to be able to process usually single-threaded operations, because the operations on the master node are synchronized and done in sequential order to achieve consistency, and then some amount of memory depending on how large your cluster is and how much data you have in that cluster. Usually it's not much. Then we have the data nodes, the workhorses of your cluster. Those are the ones that keep the data, the partial data, so the shards of the indices, because indices can be divided into structures called shards. And you scale it basically by adding new data nodes. There are different architectures around that, but basically if you need more processing power and your current cluster is not able to provide the performance it needs, or handle the data you have, you need usually more data nodes. Those nodes are heavily consumers of resources. So I/O is very important. The faster I/O you have, so SSD disks are your friend, the better. Memory, depending on how large your data is. And finally, the CPU to process the partial data that the data nodes have. Then the newest type of nodes inside Elasticsearch are the ingest nodes. First, I would like to ask a question. How many of you here are doing log centralization in your companies? Sematext, hands up. Okay, so as with backups, I know we are developers, we like to grab, or DevOps, we like to grab through the files. But believe me, a few years back, I was at the point where I loved to grab. I now don't like to grab. I just go to a certain site and search through the logs. It's way easier because I can see more than just grep tells me. So the ingest nodes can, getting back to that, can give you an idea of, can parse your raw logs, for example, Apache logs. For most of us seen any kind of logs that is not structured, a certain line in a flat text file that goes to, contains some information like IP address, path, date, and so on. Ingest nodes can take a message like this, grok them, so parse the data with regular expressions, for example, and produce out of the data certain structure that allows us to analyze the data and search it properly. Finally, the client nodes, the front-facing stuff that is there for our cluster. Those are the nodes that you talk to, that your applications talk to, and they process those queries, those index operations, and pass them on to the appropriate nodes inside the cluster. So if a query comes in and it needs to access 2/3 of the data nodes, then the client node will be the one that will do this gather and scatter phases for the queries and just pass on the data forward to the nodes and then backwards to the client. Thank you. When it comes to Elasticsearch, there are a certain amount of tuning one needs to do to have a perfectly working cluster. We'll start from top level and we'll get slowly ending on the Docker containers, which Stefan will talk about. But starting from the top level, the architecture one, before rolling into any kind of Elasticsearch-based solution, we need to think about a few points. Do we have, for example, time-based data like logs? If yes, maybe a hot-cold architecture is nice. Not to give you too much details currently, but the idea is to have some parts of the nodes on a better hardware to analyze the data, to index it, the hot new data that is currently going in, and the other part of the cluster on a slower hardware working as an archive that is rarely accessed, like once every day, once every hour, or stuff like that, when the idea behind the hot data is that someone is constantly looking at it, looking at these constant graphs that are changed, like the hot thing currently. Of course, we need to remember about dedicated masters. As I've mentioned earlier during that previous slide, if we won't have dedicated masters, the cluster is vulnerable to network splits, for example. A network split will corrupt your data in most cases. So do not go that way, people. Resource duplication, we can, the shards, you remember I was talking about the shards indices. Index is a logical structure inside Elasticsearch, and the shard is a physical data on the disk stored there in that Lucene index, inverted index format. By resource duplication, we can have shards can have two states, leader and a replica. If the leader is responsible for accepting the data, and then it passes the data on to replicas, and that way we can have a redundancy and have more throughput if we have more hardwares. For example, if we have a single leader shard and a replica, then we have two physical copies of the data. If a leader falls down, then a replica can take its role. If we have 5 replicas, then we can spread them around the cluster for each shard, and we can load balance. Actually, Elasticsearch will do it on its own. We'll load balance the queries around, so we'll have a higher throughput if our hardware allows for that. Of course, we need a proper hardware. It's not that we'll take a single ARM core and Elasticsearch will work well. So we need a hardware that will be able to process our data. The more complicated the data is, the harder it will be to go. The more data we have, the more processing power we need. That's normal. And the right number of nodes. Again, if we want petabytes of data, we need a dozen of servers there to be able to do that right. Oh, thank you. Next is the index level. Sorry, the party yesterday. The index level, the virtual being inside Elasticsearch that groups our shards and provides us with a view on the data, like the mappings, the structure of our data. Again, we can tune Elasticsearch here to some extent to work better with our use case. Again, if we are using time-based events like Facebook posts, like social media data, like logs, for example, this is where actually Elasticsearch shines. Then we can use approaches like time-based indices that we slice the index and roll it every day. So we have the new index every day to allow for a better performance from Elasticsearch, like no expensive merges, and so on. But right now, because the time-based indices are usually not equal in size, you can imagine that during a normal day when you gather logs, when there is no events around, the log flow is constant. But for example, when Christmas happens or something like that, then we have a spike. Black Friday, right? Spike of users, and then it comes to a place where the indices are not even. Some have more data, some have less data, and then Elasticsearch may work slower on those that have more data. So that's why the so-called size-based indices can be introduced to roll the index, so change the index and create a new one every time an index is at a certain size, like 10 gigabytes on HWS, and just roll over the index. In 5x, Elasticsearch, the newest Elasticsearch versions, that's automatic with the rollover API. There are also a few things like data refresh, so how fast you will see your data after sending it to the indexation. Lucene and Deuce Elasticsearch is not a real-time based system. They are so-called near real-time. And that's why you pay the price of performance if you want to have your data fresh. We did some tests actually quite a long time ago, and we were looking at the indexing speeds. For example, if we wanted to have the data refreshed every second, we had the baseline of, let's say, 2,000 events per second indexed on a single machine. Then when we increased that to 5 seconds, we got a 25% increase in throughput, and increasing that to 30 seconds gave us 75% increased throughput to the baseline, so 3,500 events per second. So that's a noticeable difference depending on what we need. Finally, proper mappings. Just do not explode them. If you do not need some fields, remove them. There is some analysis configuration that can be done inside Elasticsearch. Again, do not do too much unless you really need it, because that all counts. All those calculations needs to be done by the CPU, and we just waste CPU processing power to calculate unneeded data. And finally, I think the last note, the last thing for Elasticsearch is the node tuning. So node level, like all the JVM applications, we need JVM tuning. Usually Elasticsearch comes with the out-of-the-box Java startup parameters, which are quite good. But as usual, they may not be good for your use case, so keep that in mind. That counts, of course, this counts for garbage collection as well. Monitor that, monitor what's happening inside your JVM, and if the tuning is needed or not. And there are Elasticsearch things that you need to look at. For example, thread pools. If you have highly query-based environment like e-commerce shop, then you will need to tune the thread pools to allow a bit more queries compared to the indexing. For example, on the other hand, the log on time-based indices are usually more about indexing than the queries itself. Caches, as usual, some static information, not the caches like the varnish cache that stores the whole results. They are just a different level of caching, like filters on the shard or on the shard and a segment level that allows you to store some parts of the results to speed up your queries execution. And circuit breakers, the functionality that allows you not to control Elasticsearch and not run into memory issues like explosion of the cluster because somebody ran a query that is just too large and too heavy. Actually, one more thing. I forgot about it. We have a Linux here, right? So operating system level, that's connected to the Docker containers, which we'll just get back to. So file system limits, remember about that. Elasticsearch uses memory mapped files, so it needs a lot of file system handlers. We have the memory limits, and the more you leave for the OS caches, the better. And finally, the networking. Elasticsearch needs to know about that and definitely say about, and Elasticsearch needs to know about the nodes, and they need to see each other, so be able to communicate with every node between them. Sorry. And finally, say no to swap. JVM doesn't like to be swapped at all. So if you are in a situation where the JVM memory will be swapped, then your performance will suffer greatly.
Yeah, now we're going to put that in a container, and we have the situation we need to tune the container for Elasticsearch. We might need to or want to run multiple containers of Elasticsearch, so we could use CPU and memory limits to make it possible that two Elasticsearch nodes share the resources of a bigger machine. We have to tune the networking or provide a virtual network for Elasticsearch so that the different nodes can connect to each other. And we might need to set up security, for example, to access the files for the storage. So looking back to all the layers that we have to tune, it's not just running a container. We have to start with the operating system and tune our Linux operating system to have good I/O throughput on the disks. It needs efficient caching. And the next level is then configuring our orchestration tool, or Docker, and creating the right storage volume, and thinking how we want to persist data. There are different ways with different storage drivers. And you could create a volume that's basically a container that contains only data and is not running any process. Or you could mount simply a directory on your server node. And because we need this tuning for every machine that runs Elasticsearch, let's talk about running in production and having the need of a high performance, we should tune every server. So this means we cannot simply start some orchestration tool like Docker Swarm or Kubernetes and say, okay, let's run Elasticsearch somewhere. And that's why we suggest to mark every node that we have prepared for Elasticsearch with a label. The orchestration tools allow to define label selections, and you can start the container and say, okay, one there where we put the label, for example, Elasticsearch on it. And so you might have 10 cluster nodes, 5 are marked to run Elasticsearch processes, and then the cluster scheduler will choose those nodes which are prepared for Elasticsearch. So this is using labels. You moved ahead? One example for this machine tuning before we start Elasticsearch is that Elasticsearch has some checks before it starts, and there are some Bootstrap checks, for example, for the mapped memory files. It needs this setting in Linux to increase this value to work correctly. So they check it at the boot time, and when we start a container, our operating system should be ready for it. So we have to run some Linux command to prepare such settings before we can start the Elasticsearch container. Often you see in the web some workarounds like using single node setups, but I think that's not the right way if you want to run it in production. Configuring storage, this really depends on your hardware. You might run on bare metal, you have your disks in your computer, or you run somewhere in the cloud, and you have to attach some virtual volumes from your cloud provider. But basically, you need a directory where you store your data. So at least it is something like make directory for Elasticsearch. I have some doubts about all kinds of storage drivers that use network connections, because storing Elasticsearch files in remote directories means we get additional latency for every storage access. And this application accesses storage permanently. And this will make our cluster slow. Or imagine that we have 10 or more nodes that try to access in parallel the same network storage, and the network might become really the bottleneck of the I/O. So finally, in this example, we go and label them the prepared node for Elasticsearch. I made here an example with a Docker Swarm. And so we say Docker node update, add a label, role Elasticsearch on my first Elasticsearch node, and then it should be ready to run my first Elasticsearch instance. Maybe at this point I have to go a bit in the history. So this is a stack file. It's made of Docker Compose. Docker Compose is a YAML format where you can specify all settings for container, and with an orchestration tool like Docker Swarm, you can use such format to create your infrastructure. So you can specify multiple services, you can specify network drives, you can specify limits for your containers, and how the services are connected together. So we see here at the bottom, we put first some container limits, like using only 1 GB of memory. And the interesting part is now, if you look to the Java settings above, where do we have it? There's ES Java options, XMS 512 megabyte, and XMX also 512 megabytes. So we fixed the size of the Java heap memory at that point. And the story behind this, we got once asked, let's run Elasticsearch in container, and usually I recommend to put some memory limits on it. But what happened was that the Java has a bug. So when you put container limits on it, some Java version have a memory leak. They are not aware of containers, of Linux C groups, and so on.
It's not a bug, it's a feature.
Yeah, it's very optimized to run alone on the machine, Java. And I think there is some change in Java 9. It will be aware of container limits. So that's going to be beautiful when you start a Java process in a container. It will be aware of the limits somebody set. But currently, that's not the case. And so we have to tune the Java settings together with the container environment settings. If you forget it, you might start your container, and then you see in the monitoring tool the memory fail counters increasing. So and your Java process dies, and Elasticsearch dies, and your data might get inconsistent. That's all a big trouble if you don't take care about this issue. On the top, we see that we can pass any Elasticsearch parameter to the Elasticsearch command line. So Rafa was talking about tuning parameters. We would have here settings like this node is a master node, or it's a data node, and stuff like that could go in here, because we could pass in the command line every setting that is allowed in the Elasticsearch configuration file. Another setting in the environment here is we use here something called SPM token. That's for our monitoring tool. And the monitoring tool is clever in that way that we just label our container with this ID. And then when the Elasticsearch process starts, our monitoring tool discovers, okay, there is one container having this token on it, and then it can start recording the performance metrics and ship it to our service. Another thing here is then the volumes. So we have to set up storage. You could either use a container volume, that's what I did in this example, or you use to directory in the volumes definition for just specifying a directory on your node where the Elasticsearch data is stored. the tricky part with Swarm here is normally you see on containers that we expose a port for a network service. We don't do it here. You might wonder about that. The reason behind it is that we use here DNS Roundrobin. So when we start the first Elasticsearch container, the second one will use the same DNS name to find the other Elasticsearch node, and Docker Swarm will return another IP address, and that way it finds then the second Elasticsearch node. So therefore we have defined here in the deploy endpoint mode DNS Roundrobin. And in this setup we use a global service because we said, okay, we will not run multiple Elasticsearch instances on a single node. We are going to have a setup where we have dedicated Swarm cluster with defined for Elasticsearch, and a global service in Swarm means it will put the service on every node that joins the Swarm cluster. And the last thing here is the placement constraint. We see here node labels equals Elasticsearch, and this means the global service will only deploy to nodes which are prepared for Elasticsearch. I think that's the thing about this compose file for one service. Such a compose file can have more services, and as I mentioned, we couldn't specify a port for the global service using a DNS Roundrobin in Swarm. We made an entry point. This is just the Nginx web server as proxy definition to forward traffic from this port 80 to the Elasticsearch cluster running in the Elasticsearch network on Swarm. So Swarm creates an overlay network. Imagine you have multiple nodes, and when you start such a stack, the nodes are connected with an overlay network. So the processes defined in these containers can communicate via this overlay network, and the container will be reachable with the name of the service called Elasticsearch on port 9200. So that's kind of workaround with the Swarm networking. If you use different orchestration tools, you might solve it in a different way. On Kubernetes, you could simply use the Kubernetes Proxy to handle that. We have here some more things, but we have some more things here. We have the deployment strategy. That's also something you can define on containers in Swarm. We could say, okay, if it fails to start, maybe Elasticsearch is not ready when Nginx starts. That's the reason here. Just restart it after a few seconds, and maybe Elasticsearch node is then up, and then it can start a proxy service to it. Okay, next one. We have then just our monitoring set up to collect all logs, metrics, and events from Docker, and also connect our client to every Elasticsearch node, having a monitoring agent that connects to it, doing some automatic setup using just a Docker socket. So it sees automatically new Elasticsearch instances started, and then it starts monitoring. To deploy this stack, you can use the command docker swarm deploy. And it converts the Docker compose file to a so-called bundle file for Docker Swarm. That's in JSON format. And it starts then a stack, and we see then multiple services starting, one for the Nginx proxy, one for Elasticsearch itself, and two others for the monitoring of this system. So now we want to scale and use more Elasticsearch nodes. What we have to do? We have to create a new machine. We have to tune it, do the Linux tuning, the file system settings, and then we can install Docker and join the Swarm cluster. And once we are done with the tuning of the node settings, we can attach the label, label role Elasticsearch, and in that moment, Docker Swarm will recognize this node and sees, I have a global service to deploy Elasticsearch, and the label matches, and then it will deploy this service to this new node. So scaling then Elasticsearch, it's easy as creating new nodes, joining the Swarm cluster, and an additional node will be deployed. So we're at the end of the example, and with this procedure, deploying Elasticsearch with one orchestration tool, and there are other issues with other orchestration tools, we will learn several things. We cannot simply take Elasticsearch, put it in a container, run it, and expect it has good performance. We have to tune every Linux node. And there was no tool like, most of the things that we did, we could replace tools like Ansible, but there are still a few commands that we have to run on every node, and so we still depend on other deployment tools to do this before we get into the Docker world where everything is simpler. The next thing, bit disappointment was meeting such bugs, for example, in Java, or not being aware of doing the right configuration for Java. And this is another little bit of pain point, because as operator of the system, I can't say, okay, let's give Elasticsearch more memory, and I redefine the memory limit to something like 32 gigabyte instead of the 16 gigabyte. And I must be aware that I have to change the Java memory settings at the same time. There are some interesting tools coming up that is watching the inside of the container. You can figure out the limit set that's stored in some Linux-specific directories. And some people made then scripts that read this limit and start then Java with the right settings. So there's some way to automate this process of making Java aware of the memory limits. Then the second problem was I was playing around with this DNS Roundrobin thing and the Nginx proxy service to make the networking for Elasticsearch working. And that's also a little pain point. If you know Elasticsearch for a longer time, there was in the past the Multicast Discovery, and it was quite easy. You started one Elasticsearch server on one node and somewhere else, and it was finding each other via multicast messaging. The problem with this setup in production was sometimes the developer notebook just joined the production cluster, and this turned down really the performance of the production cluster. So accident like that happened if somebody was in the wrong network and just started somewhere Elasticsearch node. So the recommendation was to disable multicast discovery. And in Elasticsearch 5.2, I think it got completely removed. And on Docker, we are in a different situation. We have here our code as infrastructure. Means we coded the network and say, this is a dedicated network only for this Elasticsearch. And here it would be nice to have the multicast discovery again, so we don't need to do special workarounds to set up the nodes so that they find each other. The good thing about Docker and Elasticsearch, once you have done your setup, it's portable. So maybe you don't have not this log to a specific cloud provider. And the community is great, both Elasticsearch and Docker community. There are people looking for solutions. And especially on Kubernetes, there is a tool called Operator. And this allows to extend Kubernetes with a, let's say, custom command set. So there is a tool called Elasticsearch Operator. Looks very promising. It's very new. And tools like that will automate the complete process much better.
So as you can see, with both those tools, let's call them, we are not there yet to say that this is a love from the first sight, but we are getting there. The relationship is getting closer and closer, so they will love each other for sure. For now, it's as Stefan mentioned, it's a bit of a pain point. And but if you would like to try, go ahead. It's fun, as usual, with all the new tools. And this is actually all from us for today. It was Stefan, I'm Rafal, and if you would like to play with tools like that and make use of that during your normal work, come to us, come to our booth, talk about the jobs. We have a few offerings down there. You'll work with crazy people. with a very nice company. And come, if you have any questions, you can ask them now. You can ask us at the booth where they're available for you to talk, chat, and later in the club for a beer or something like that. Thank you very much and enjoy the conference.